Alright, we're going to start out with section 2.2 here, dealing with density curves and normal distribution. So we're going to talk about density curves first to start out with this. So we've got our density curves. Okay, so we're going to start out talking about here. Now, with this, let's think about this. So a density curve is going to mean that everything in the area is going to add up to 1, right, or 100%. So for this, let's think about rolling a die, right? So you roll a die, and there are 6 sides to it, right? So with that, let's draw this out here. So we got a line here, and we got going at 1, 2, 3, 4, 5, 6. All right, so there's 6 sides, right? So if we were to do this, what is the probability of getting any one of those sides, right? Getting a 1, getting a 2, getting a 3, all the way to a 6. Well, if you think about it, there's 6 sides, you roll it, you have a 1 in 6 chance, right? So with this, we're looking at, so up here, on the height, we're talking about 1 in 6 chance, right? So you have a 1 in 6 chance of rolling any one of these numbers, okay? Any one of those numbers, in which case, inside there, the density curve area inside density curve area is equal to 1. Because each one of those sections in here, if you were to cut this off and then add them all up, would equal 1, right? Because if you were to do this, cut this off, and you have a section of 1 right here, right? Then you have a section of 1, and so forth, right? So if you were to add up, your area is your length times your width. So our area is simply our length of 1 times our width of 1/6. So if we add that up, our area would then equal just 1/6, right? Well, if we add up all of those areas for each one of those rolls there, it should equal 1. Because we have 1/6 plus 1/6 and so forth, all right? We did this 6 times. So 1, 2, 3, 4, 5. And that would equal 6/6, which equals 1, which would give us our area. So, again, they have all the same probability under this density curve, and the area should all add up to 1. Now, with this also, when you're looking at this as well, your median and mean, alright, so they should be pretty much equivalent to each other, right? About the same. So your mean should be about the same as your median, if anything. And that's what you got to think about this when you're moving forward with these type of problems. We'll go over an example here when you're thinking about this, okay? On how to play these out. So let's do this. So building our density curves, let's start our problem. Let's say you're waiting on a red light that turns off between 5 and 10 seconds. So every time this red light blinks on, it'll stay on for about anywhere between 5 and 10 seconds. So if we're to draw this out, okay, So let's start out. We got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. 1, 2, 3, 4, 5. 5. So what we're saying is this light stays on between 5 and 10 seconds before it'll turn off. Okay. Now with that, therefore we have how many spaces here? We have 5 spaces right here, right? Well, and if we're going to do this, they all have the same height, right? So therefore, the height for all of these, if you divided these into 5, would be the 1/5. So I have a height of 1/5. Okay, so now if we've got this data here, we understand that there's 5 sections here, all the same height, so they each have the same height of 1/5 with looking at this. About what percent of the time will the red light turn off more than 8.75 seconds after it is turned on? So in other words, it's turned on. So we want to know what percent of the time will the red light turn off more than 8.75 seconds. So 8.75. Okay. Seconds. Okay. After it is already turned on. So with this, let's think about this. We've got to go, we need to find the width of this range right here. We need to find, I mean, right, 8.75 different area. So it's 8.75, you all saw that. So we're going to say that you got to find the width of this area right here, right? Well, that's pretty easy. I'm pretty sure y'all can see that. We can simply take the width. Since we know we have 10 seconds total, and we're actually going, it says 8.75. So therefore we should have 1.25. seconds. Okay? So our width is 1.25 seconds. So now I just want to know, again, what percent of the time? So what percent of the time will that actually play out? Well, if we know the width is 1.25 and our height is 1.5, can we just find the area inside there, and that would tell us the percent of the time that it would happen, the area of the time, which is the percentage of the time that it happens. So if we took area, which is simply length times width, and we know our length is 1.25 times our height. Well, I'm sorry. We just said our width here, length and width. But length and width, 1.5. So in this case, we've got 1.25 times 1/5. So the area overall, if we put that in the calculator, so 1.25 times 1 divided by 5 That should give us 0.25. In other words, saying 25% of the time is when it happens. So we could simply say that 25% of the time the red light will change after 8.75 seconds. Alright. Let's do another little problem I wrote down here. Let me see. So let's calculate and interpret. So if we're going to do this, let's calculate and interpret the 65th percentile of the distribution. So the 65th percentile of the distribution. Okay. So to determine that, first off, we know 65th percentile, well, that's your area, right? We're just talking about the 25th percentile over here for 8.75, or sorry, greater than that. So 65 percentile of the distribution, we're going to say that our area is 65%, because we want to know the area from 0 to the 65% time frame. So we want to know the area from wherever here to wherever the 65th percentile. Okay, we want to know that value. We want to know this value, right? So we know the area is 0.65. We know our height, or our width in this case, we could say is 1/5. And we're wanting to know our length, alright? So if we were to take 5 times 0.65, we should get 3.25. So our length should be 3.25. Now the trick here with this is, again, the light wouldn't start, or wouldn't have a possibility, shall we say, of turning off until 5 seconds. So you need to make sure that in the 65th percentile you add that 5 seconds. So we're simply going to take that 3.25 plus the 5 seconds is 8.25 seconds. Okay? So we're looking at 8, and then my 0.25 is right in here. That is 65th percentile. And to interpret this, we would say approximately 65% of the time. So approximately 65% of the time, the red light will turn off. Will turn off before 8.25 seconds. The light will turn off before, keyword before 8.25 seconds. Because we're saying the 65th percentile, so 65% of the time it falls below 8.25. Anywhere from 5 to 8.25, it falls 65% of the time. It falls in that range. Okay? Hopefully that makes a little bit better sense on density curves. Now we're going to talk about real quick as far as normal distribution. So normal distribution is simply our normal curve. Alright, so our normal curve is just a bell-shaped curve. Okay. Normal bell-shaped curve. In which case, when you label these, every time you label a normal curve, you can simply put an N, and then you're going to put the mean, that's a mu, Greek-letter mu is for mean, and a lowercase sigma for standard deviation. Again, this is your mean, and this is your standard deviation. This is key label to a normal curve. So even if you were to make it look a little crazy, not so normal looking like mine, as long as I put that N and then my mean and my standard deviation, that verifies that it's a normal curve. Now, with this, there are normally 3 standard deviations above and 3 standard deviations below is what consists of everything, for the most part, under a normal curve. So let's say our mean is here, and then we're going to go up 3, we're going to go down 3. So we're going to say mean plus 1 standard deviation, we're going to say the mean plus 2 standard deviations to the mean plus 3 standard deviations. On this way, of course, the opposite, mean minus 1 standard deviation, the mean minus 2 standard deviations, and the mean minus 3 standard deviations. Now, easiest thing to get confused with, and a lot of people forget about, is what percentages of the data falls between each one of these standard deviations. And with that, between 1 standard deviation, 68% of the data will fall within 1 standard deviation of the mean. Within 2 standard deviations, you have 95% of the data falls between 2 standard deviations of the mean. And then from your 3rd standard deviation or your minus 3 standard deviations to the positive 3 standard deviations away from the mean, you're looking at 99.7% of the data falls within 3 standard deviations away. So what do you have left then? You have just your 3%, right? 3% is left. You're like, where's that 3%? Well, that counts up in the tails. But since you have 2 tails, you have to remember that you've only got 1.5% here and 1.5% on the upper end. So in other words, altogether, it's 100%, but these tails include 1.5% of the data that you're looking for in a normal curve. So if you're to break this down, so we'll make this so you can split this up, see how this plays out. Okay. Let's say we got our mean right here. Okay. And one standard deviation, two standard deviations, 3. 1, 2, 3. So if we said we have 68% between one standard deviation away, so let's put 1 and -1 because that is technically your z-score, right? Your z-score is going to be here. As far as one standard deviation above, or negative one standard deviation above, that's 68% of the data. Well, if you divide that by 2, you should get 34% on each side of the mean. Okay? And then if you're going to go from -2 to 2, and that counted for 95% of the data. Well, since we already have 68 involved with the first standard deviation, that means we just need to put the rest of our data, which would be 13.5% on this side between one standard deviation and 2, and 13.5% between -1 standard deviation and -2. Okay. Then going on to the third, and our -3rd, we're sitting at 99.7%. So between the second and the third standard deviation, you should have 2.35%. 2.35%. And since we still just have that 3% on the end, we should only have 1.5% of the data will fall under the lower end tail, and 1.5% of the data will fall on the upper end. Make sure to understand these percentages and how this plays out, the percent and area underneath the curve, because these are very common questions that will pop up on AP exams and just exams in general for statistics. Make sure you understand the 68, 95, 99.7. And I always make my kids do it when we do face-to-face. When you touch your head, it's 68, shoulders 95, all your hands all the way out, 99.7. So you always think 68, 95, 99.7. And it helps you remember it a little bit easier. But that is how that's going to play out. Again, this is a normal curve. What did I forget to put on this curve to make it normal? The key. So the key for this guy would be, it's a normal curve with our mean, comma, our standard deviation. And that would verify an actual normal curve with that. Okay? And one other thing I just want to talk about real quick, and that is just dealing with the different shapes that we have and how the mean and medians work out. I think we kind of discussed this a little bit. We're going to talk about it one more time. So if we have symmetric, we have a symmetric curve, all right? We're going to be looking at our mean and our median being very equivalent to each other, right? They should pretty much be the same. if we're going to do, let's say we have a symmetric setup as well. It's still symmetric, but instead of unimodal, it's bimodal. So let's say you have this. So you have a curve like that. Even with having bimodal, the mean should be pretty equivalent to the median as well. Maybe not always spot on number, but very close to one another. Alright, and how it gets a little bit different is, let's say you have skewed right. So we have skewed right. So again, think about your right foot. So your right foot, you got a big toe, and it comes down and goes a little pinky toe, right? On this, with skewed right, your median is going to be less than your mean, right? Here's your median. And your mean is going to be somewhere over here. Because you have this tail is pulling, there's higher number of data values here that are pulling the mean to the right. So for this, the median will be less than the mean. Alright, so now let's say we got a skewed left. So skewed left, the big toe starts over here, and it drops down and goes something like that, right? Now your median is going to be where that peak is. It's your median. It's a higher value. However, your mean is going to be pulled lower because you have these values of these lower number values over here, right? So you got your mean, in which case we're simply saying that your median will be greater than your mean. Greater than your mean. So horrible greater than sign, I'm going to fix that real quick. Okay. So Pac-Man's eating the bigger numbers. So Pac-Man is eating the median there on the skewed left. The mean is greater on a skewed right. And then symmetric, your mean and medians are pretty much right at the same. Alright, so hopefully that explains a little bit. That was a lot in this one little lesson, but had a lot to cover. So hopefully that helps out with the problems on your check your understandings. I'll see you guys next time.